So today our webinar is going to focus on using SolidWorks Motion to analyze motor sizing for mechanisms. So today's demo is going to be on the Holmatro spreader, which is a vehicle rescue spreader, kind of pictured there, shown there in the picture. And what they use this for is, you know, after car accidents and things like that, they use them to you know, bend metal and spread metal to rescue survivors. So with today's webinar, if you have questions, you know, your participation is encouraged. You know, ask questions. I have some panelists that are helping me out, so if you have questions, feel free to type those in the question box in the GoToMeeting toolbar, and we'll try to answer those questions throughout the webinar if they're appropriate, or we'll also have some time at the end of the webinar where some of those questions can be answered as well. And then we'll also include our contact information at the end of the presentation, so we can you know, follow up with any questions that we still have outstanding. So so I will jump over to SolidWorks and kind of begin the presentation. So like I said, today we're focusing on motor sizing for mechanisms. Now, motor sizing can actually encompass many different types of motors. Okay, so in this case, the Holmatro case, they're actually using a hydraulic, you know, a hydraulic actuator. But this will, you know, the same type of analysis would apply to electrical motors, linear motors, as well as rotational motors. We can analyze the force required and those sorts of things. So with SolidWorks, you know, everything I'm showing here is actually can be done with SolidWorks Premium, just out of the box. Otherwise, if you have SolidWorks Standard and SolidWorks Professional along with Simulation Professional, you can also utilize motion and simulation, which we'll be showing here. So I kind of want to do this one a little different. I want to jump over to my results and just kind of show you some of the things that we can get with this type of analysis, and then I will jump back and show you what I went through to set that up, or to set the analysis up, and kind of guide you through that process as well. So the first thing to sort of point out is SolidWorks Motion actually depends on your SolidWorks mates. Okay, so you see we've got a whole list of mates here that are used, you know, to build up your assemblies, but also to control degrees of freedom on parts to allow any movement. Okay, so if we look here, if I grab just the plunger here, you can see that you know, as I move that, we can see that the spreader is moving or opening. The jaws are opening up, but you'll also notice that if my my blocks are not moving when the jaws are opening. Okay, so we need to kind of set up some additional things within motion that allow us to detect that contact between the test apparatus as well as the product being analyzed. Okay, so motion simulation is another add-in in SolidWorks. So if I just go to Tools, Add-ins, and pull over my window here, you can see that I have added in SolidWorks Motion as well as SolidWorks Simulation, which I'll get into after I run the motion analysis. Okay, so jumping over, so motion is actually, the motion setup is actually done sort of in this lower panel. And when I click on this Finish tab, this is my Finish simulation, just showing the motion tools, my results tools actually right now, and all the things that I've set up. So just kind of to guide you through what we have here, we have just a simple actuator. Again, I'll show you how all these are set up. We have a couple of forces on the blocks, some reaction forces that would be provided by the test apparatus, and then also the solid body contact. So you see my blue and pink parts. That's where we're detecting any contact between anything that's not controlled with our mates. We've also set up gravity to keep everything kind of in place, and then simply, after we set all these things up and then we solve the analysis, we can get kind of our resulting animation. So I'm just going to, again, this is already solved, so I'm just going to play this and kind of show you what we can see. So, as I play it, you see that the jaws are spreading and it's pushing against these testing blocks that again have a reaction force that are associated with them. So simply just animating that motion by actuating that piston. I can quickly rewind it and play it again. So if we go back and we can speed this up a little bit, I can hit play and notice the piston's moving, which is controlling all the motion of the rest of the assembly. So, after we get that, of course, we get the animation and we can actually visualize the motion, but we also can create some different types of plots. So the first one I'll show here is my actuator plot. Okay, so this is actually the motor, the required force throughout the motion. So because the actuator is just moving in the linear direction, it's actually spreading those blocks, and our reaction forces are kind of changing throughout the motion. So we kind of see this unique plot, showing how our force required on that actuator is actually increasing as we move along, all the way up to about the 3-second mark. And then as it gets wider, the motion required, or the force required actually decreases. Another plot we can look at is our reaction force plot. So this may be a little hard to see because it's actually ending up right here on this line. But this is actually the reaction force between one of the tips and a block. Okay, so we can kind of see the reaction force is approximately 4,700 pounds as we see it here on this. So that increases as that force increases and then becomes constant. So forces are definitely something we can find with this type of analysis. Forces required, contact forces, reaction forces, those types of things. Now, motion is a rigid body solver, so the bodies that are interacting cannot deform in any way. Some of you may be familiar with simulation, or SolidWorks simulation, which is a deformable body solver, which allows us to actually calculate how the bodies will compress and deform under a loading case. Okay, so once we've solved the rigid body motion, again, if I pull up this plot here, we can kind of see at the 3-second mark we have sort of our maximum force required. So here we can sort of consider this as potentially our highest, the time step with the highest loading on one of the arms. So if I bring this back to that 3-second mark, I just pull that back to my, on my timeline, I just pull that back to the 3-second mark, and I can actually show my stress plot. So I've actually gone through and set up an analysis on this arm here, and then if I show my stress plot, you can kind of see we can actually get stress values on a single body as well, following a motion study. So here we can see the stress values. Sometimes it may be a little hard to see when we don't have, or when we're showing all the other parts. So I can actually grab that arm and then just isolate that arm, and we can actually analyze, the stress on this single arm here. Now we can also look at, a plot for deformation to see sort of how this is deforming. We can see that value here on the top right. So we're deforming about 0.001175 inches. And then we can also show, factor of safety, where a factor of safety of 1 is actually, at the yield point, and then if we have a factor of safety above 1, that means that our design is safe. So we can see here that our factor of safety is 2, and actually goes up to an extremely high value, 742, where we have a very low loading out here. So these are the types of plots we can see within the motion analysis and using the simulation add-in as well to analyze any point in time in the motion analysis. So again, those are the types of plots that we can look at. Now let's get into and see how I went about setting that up. So what I'll do is I'll jump over to this other motion study that I have set up with really no setup done in the model yet. So again, the first thing we need to add is that linear actuator. So all my tools for motion are actually located across here above our timeline, and for this type of analysis I want to add a motor. So I'll just click the motor, and you can see I can choose from a rotary motor type or a linear motor type. In this case, it's just a linear motor because we're moving one body in a single direction. And then I can come in and choose my application location, and you see the arrow kind of signifies what direction, so it's actually going the wrong way, so I'll just flip it so it's going in the positive X direction. And then what I'll do is I'll say I want that motor to move a distance of 2.25 inches, and then do it over our 10-second time period. I can click OK there to add that. And then the next thing to do is to add our the testing apparatus forces. Okay, so this spreader needs to be able to spread apart a force of 4,500 pounds, kind of acting on each side. So to add an external force to this, we simply choose the force tool here. And you can see we can add a force or a torque if it's rotating, but I'll add a force here. We'll do action only, and I'm going to put in the push pin because I need to add one to each side here. So my first selection is going to be, where I want that force to be applied. Again, it's going in the wrong direction. I want it to be pushing that block, kind of counteracting the spreader from opening. And you can see there we just flip that, and now it's acting toward the spreader. And then I give it a value of 4,500 pounds. And that's just a constant force. We can add a function, have that change over time as well. So I click OK, and that adds the first force, and then I'll add the second force on that side. We see it's going in the right direction, and then I can just add 4,500 pounds. I can remove the push pin and hit OK. Okay, so you see down here on the bottom, you can see that our motor has been added, and then the two forces. So the next thing we need to add is our contacts. Okay, so our contacts, again, when I showed the example of just moving that piston, we saw that there was really no mate that's constraining the blocks. The blocks kind of just sat there, and the spreader was allowed to pass through them. Well, if we add a solid body contact, that won't allow the tips to pass through the blocks. Okay, so I'll add that. We'll just do a solid body, and we'll use contact groups. So I'm going to pick my blue group, which are the tips, and then I'll pick the pink group, which are the blocks. And you can see, if I scroll down here, that it's actually detecting 4 contact pairs. So it's actually, when we do it this way, it's actually saying this blue tip can contact that block or that block, and then this blue tip can contact that block or that block. So it's actually 4 contacts. We could individually set these up on each side, but this can be done in one single contact set. I'm just going to adjust this to kind of a steel material. So we've got metal on metal, just so we can see my impact, my impact coefficients down here. And then I'll actually turn that off so I can adjust that and turn off the friction as well. So we'll ignore friction. And then when we turn off the material and friction, we actually can manually edit these values here. So you see once you select a material, it actually defaults to that stiffness between the two materials, and then also gives us an exponent that controls the equation being solved here. So there's two different types of the manual contacts that we can set up. They're based on impact calculations and also a restitution coefficient equation as well. So these two equations are actually explained in the help menu, which if I simply push this question mark, it'd bring me right to that page where we can read a little bit more about what's going on. So in this case, I'm actually going to make the stiffness and the damping the same. And when we have rigid bodies, to sort of ease allow the solver to kind of ease into the calculation, we can allow a tiny bit of penetration, so those bodies can actually pass through each other by a very tiny amount, 0.0039 inches, 0.0039 inches. Okay, so that's how we set up the contact. And then lastly, I mentioned gravity. In this case, I really don't need gravity, but we can turn it on just to show. Because we have these slots, it's actually kind of keeping everything set in place. We have mates that are holding the main assembly in place, and then also the testing apparatus. But just to show how to apply gravity, we can click that, and then it's just a simple select what direction. And then over here on the right side, you can see we've got gravity pointing in the negative y direction. So I can click OK. And at that point, it's simply clicking the Calculate button. But before I do that, I guess I do want to show some of the motion study properties over here. So if we jump into the motion study properties, you can see that we can solve, a very, very coarse motion study, or we can solve a very, very fine motion study. So, the default value is 25 frames per second. If we do a coarse study, we can, move it down to, let's say, 5 frames per second. We can also control some of the contact resolution. If we move this up to high, it takes it longer to solve those contacting surfaces. Or if we even turn on use precise contact, that actually is going to use the surfaces. With the contact resolution, the lower we go, the more coarse the bodies kind of are to the solver. And then we can also control accuracy, leaving kind of everything else as the default is what I'll do here. But we can control that high or low accuracy to calculate, either more accurate or less accurate, but faster analyses. Okay, so at this point, it's a matter of going ahead and clicking the Calculate button, and you'll see that it's calculating. You kind of see some indicators and some messages over here on the right, but you see it kind of calculates us through that motion. And of course, we can kind of pull this back, move it, and kind of see how everything's reacting throughout that calculation. Okay. And then if we kind of go to our click a filter, just showing my results, you'll see that my results folder doesn't really show anything currently. So to get those plots that I had shown in the beginning of the analysis, it's simply clicking a result plot here, and from the drop-down menu, just kind of picking what you want to get a closer look at. So in this case, it was forces, and then I picked motor force, and we'll say the X component because we have that X direction where we have that linear actuator in the X direction. And then I simply can come down here and select that linear motor as my component to analyze. I click OK, and you see that we have that plot, and we get that same plot there showing, at 3 seconds we have that maximum force, and it's roughly 50,000 pounds required on the actuator. Okay, a very similar process to get the contact forces. Again, we click the result plot. This time I'm going to choose forces and a contact force, and then we can select, contact force magnitude, and then select our two components. So we'll grab the tip of this because that's what makes contact, and then grab that face there. And there you see we have that roughly 4,700 pounds again, where it kind of ramps up, and once that makes contact, then you see that it's actually pretty constant, that reaction force between those two components. Okay, and then the last step, of course, was to run the simulation. And again, that's we can set this up in a few different ways. In my case, I just looked at that single time step, so I can actually drag this out to 3 seconds, and then click our simulation setup button, and you can see that we can calculate this for one component. So I choose that arm, and then because I've moved the slider out to 3 seconds, it actually sets this to 3 seconds at the start and end time. Now we can add different time steps in. So let's say we wanted to go from 0 to 10 seconds, but also show it every 1 second. So we could actually run 10 different simulations with this interface by just adding additional times. So if I add that time, we get our 3 seconds inserted in there. We can also control, again, the accuracy of this. With my mesh density, we can jump that all the way out to coarse to kind of speed it up, and hit OK. And now our analysis is ready to run. Next, we click Calculate Sim Results. No, I don't want to rerun the motion study. We already have those results. And you can see that it's going to process those results and then mesh our model and run the analysis. Okay, and then again, if I filter to my results, actually we got to filter to my simulation results, you can see that it does give me a keyframe there, meaning that when I move it over to that keyframe, you see that it shows the plot, the calculated result there. And if I move it off that keyframe, you see that our result isn't showing. So again, this is only calculating at a single time step, but we can, with that interface, we can set up to have different keyframes. If I would have went 0 to 10, we could have had one at 1 second, 2 seconds, 3 seconds, 4 seconds. But because this was kind of the highest, force, we can see that, and once once the contact forces between the two components kind of reach that maximum, we'll see the actual highest forces on this. So we picked the highest force kind of pushing on it from the piston end, and then the highest contact force, which was pretty constant after that, a half a second. We actually kind of find the case where we're going to have that highest force. So then we can, of course, visualize our simulation results from here as well. So we can look at the stress or deformation factor of safety. So that kind of concludes the short webinar. So we have a little bit of time for questions here if anybody has any questions off the top of their head. So feel free to submit a question. Otherwise, you can contact us. You can send your questions to info@alinix.com or give us a call at the 1-866-378-6829 number, and we can we can reach out to you afterwards as well. So any questions? Okay. So someone asked, can I explain the mating conditions? So the mating conditions, again, they're actually controlled with our regular assembly mates. Okay, so there's actually quite a few mates in here. You know, typical mates like you know, concentric mates for things that are round. So there are, you know, like on this component, you can see that there's a pin kind of dropping through there, or a bolt. So that's, you know, this is going to be mated to kind of the orange body, and then this arm would actually be concentric to that pin. So it allows rotation around that pin, but it doesn't allow any translation really in any direction. So there's actually quite a few mates, and this is probably the most time-consuming part of the motion simulation. So I didn't go through and show that because that's more SolidWorks stuff. But there are you know, different mates, and then you'll see there is this unique limit distance mate, meaning this actuator is allowed to move up to some limit and then back to some limit. So that's kind of what's controlling that piston, because there are definitely contacts in there. Now we could have in SolidWorks Motion, we could have set up, you know, a solid body contact between that face and that face to actually do that. But really anything we can do to simplify it on the solver we want to do. So we set up a limit distance mate to kind of control those degrees of freedom on the body. So there's another question, how to plot reaction force versus distance. So the reaction force versus distance, if we jump over here, if we edit this, yeah, let's see, we have a, you know, this contact force, or, you know, you can do a reaction force, or, you know, the motor force versus time, but versus distance, I don't see a way to do that, but we can, you know, because my motor is actually going 2.25 inches per over 10 seconds, you can actually relate the two, maybe over in Excel or something like that. So, you know, we know 2.25, so like at 3 seconds, you know, we just take 30% of 2.25, and we know what the distance is at 3 seconds.